Welcome back. We now consider some examples on the concept of this chapter. That is, how do we get the a basis and the dimension of the sum of two vector subspaces of a vector space, and also the intersection of two vector subspaces of a vector space. Okay, so worked examples. The first problem here says let P of t be the vector space of polynomials in T over R. So this is vector space of polynomials, okay, with real coefficients, okay. Suppose U and W are vector subspaces of P of T. So this is the vector space and these are vector subspaces. And these vector subspaces are generated by this set. So that means this and this respectively, implying that U is generated by this first set and W is generated by this second set. So we want to find a basis and dimension for U, the subspace U, find a basis and dimension for W, then find a basis and dimension for U plus W and also U intersection W. Okay, so let's get right into it and see how this works. Okay, so for the solution to this problem, so we're starting off with U. So when it says generated by, I mean, that means spanned by, okay? So the subspace U is spanned by these vectors, okay? So by that, we can readily tell what a basis of that vector space would look like by putting this in, using the vectors to form the rows of a matrix. We've seen that already from previous work, and then we carry out row reduction on that matrix to have a basis of the subspace U. And we do the same thing for the subspace W. Okay, so let's take them one after the other. So for the A part, we are given that U is spanned by this set. That means U is the span of the set with vectors t cube. Of course, vectors in this case are this polynomial. So this is t cube plus 4t squared minus t plus 3, and then t cube plus 5t squared plus 5. Then we have the last one here, which is 3t cubed plus 10t squared minus 5t plus 5. Yep, we're good. So as usual, we know that we can think of this in terms of the coefficients of the terms or the expressions for t. So we can think of this as having a structure defined in this form so that it is easier to relate with the vectors. So we can think of this as the coefficient of t cube coming first. We can take this as 1. Then the coefficient of t squared coming next, that is 4. The coefficient of t coming next, that is minus 1. The constant coming last, that will be 3. Okay. Of course, we can also put it as though they were R4 vectors in this case. That is fine as well. So we just want to observe that there is a structure to this, and we can just go flow along with that structure to obtain a basis of the vector space instead of doing this from the ground up using the first principle like we did for a similar problem previously. Okay, so we know now that it's just faster to work with the structure like that. And so this is t cube. The coefficient of t cube coming first, that is 1. Coefficient of t squared, 5. Coefficient of t is not here, that is 0. Then the constant coming last, that is 5. So then we have the next one here. So the coefficient of t cube coming next, that is 3. The coefficient of t squared, 10. The coefficient of t, that is minus 5. And the constant, that is 5. So we can put them all together this way. So if u is equal to the span of these vectors, then we can easily get a basis for u by arranging this in a matrix. So we have 1, 4, minus 1, 3, and then 1, 5, 0, and 5. Then we have this to be 3, 10, minus 5, and 5. So we know then that having used these vectors as the rows of this matrix, then a basis of the row space of this matrix would be a basis, okay, for the vector space U. So that's what we now do. We will now carry out elementary row operations as expected to reduce this, okay, to put it in its echelon form, okay. Obviously, this is a 3 by 4 matrix, 3 rows, okay, 4 columns, 1, 2, 3, 4, okay, not a problem. We still follow that pattern. We'll take this, use it to eliminate everything, okay, below it. So we'll just put it in echelon form. It doesn't have to be row reduced echelon form or reduced row echelon form. So for that, we say R2 equals R2 minus R1 because that ensures that this goes to 0, and R3 equals R3 minus 3R1. And when we do that, we'll get this result. Nothing is happening to the first row. So that is 1, 4, minus 1, 3. So the second row, we have 1 minus 1, that is 0. 5 minus 4, that is 1. 0 minus minus 1, that is 1. 5 minus 3, that is 2. So then the third row, we have 3 minus 3 multiplying 1, that is 0. 10 minus 3 multiplying 4. 3 multiplying 4 is 12. 10 minus 12, that is minus 2. Minus 5 minus 3 multiplying minus 1, that is minus 5 plus 3. That will give us 2. Okay, minus 2. Okay, so this is minus 5 plus 3, that is minus 2. Then we have 5 minus 3 multiplying 3. 3 multiplying 3 is 9. So we have 5 minus 9, that is minus 4. And that is all we have for this portion. And what else can we do? We move to the next one. Okay, the first non-zero on the next one. So this is 1 here. We use it to take everything we have here to 0. Okay, so we can just deal with the number below it. And for that, we can say R3. Okay, R3 will be equal to R3 plus 2R2. So that will ensure that this goes to 0. So we have R3 to be equal to R3 plus 2R2. And when we do that, what do we get? Nothing is happening to the first row, so that remains 1, 4, minus 1, 3. Then on the second row, nothing is happening. We have 0, 1, 1, and 2. Then on the third row, we have 0 plus 2 multiplying 0, that is 0. Minus 2 plus 2 multiplying 2, that is 0. Minus 2 plus 2 multiplying 1, sorry, that is 0. Minus 4 plus 2 multiplying 2, that is 0. So with that, we are good to go. We now have the matrix in echelon form, and by this, we have successfully established that indeed the vectors here that span the vector space, yes, they span the vector space, but they have now been confirmed to not be linearly independent, and so they could not and they could not have formed a basis of this vector space because they are linearly dependent. That is the implication of having a zero row here. That is one. And with that also, we have established that these two vectors we have left, these two rows we have left, will span the same vector space as these three vectors. So by that, we now conclude that hence a basis of a basis of U is given by, so in this, that means a basis of U will have only two vectors, and the vectors will be given by this 1, 4, minus 1, 3, and 0, 1, 1, 2. And of course, we will contextualize that to what we have here. We know that the first entry is coefficient of t cubed, second is coefficient of t squared, third is coefficient of t, and the last is the constant. So we just put that out directly now. So this is coefficient of t cubed. So that means for the first vector in this basis, okay, of the vector space U, we'll have this to be t cubed, and then this will be plus 4t squared, then minus t, then plus 3. That will be the first vector. The second vector will have 0t cubed, so we can ignore that. 1t squared, so that is t squared, then 1t, that is t squared plus t, then plus 2. And that is that about that. And of course, we can also conclude that from here, the dimension of the vector space U is equal to 2. Why? Because there are two vectors in the basis of the vector space U. In a basis, okay, any basis that is of the vector space U. And with this, we are good to go. We have now completely answered the first part of the problem. So the next one is for W. We need to get a basis and also the dimension of W. So let's go ahead and deal with that now. So we're given that W is spanned by is a given set of vectors. That means W is equal to the span of, so what are the vectors? Let us write them out. We have T, that's T cubed plus 4T squared plus 6, T cubed plus 4T squared plus 6. Then we have T cubed plus 2T squared minus T plus 5. T cubed plus 2T squared. So minus T plus 5. Yep, we good. Then t cubed plus 2t squared minus t plus 5 here. 2t cubed plus 2t squared minus 3t plus 9. 2t cubed, right? We're good. So we know that it is spanned by these vectors, and we can also put that in this form such that the coefficient of t cubed comes first, so that is 1. The coefficient of t squared coming next, that is 4. The coefficient of t coming next, that is 0, since it doesn't exist in this one. So that is 140. The coefficient of, the constant, that is 6. So we can put it this way. And then we say for the second one, we have t cubed, that is 1. T squared, coefficient is 2. T, the coefficient is minus 1. Then the constant is plus 5. Okay. Then we have the third vector here. We can put it in this format as well and say this is 2. Then we have this to be 2 as well. This is minus 3, and then this is 9. Okay. So putting it in that format, we're able to now work with it. So we now say that to get a basis of the vector space now, we put this in a matrix. Or put it in a matrix, then we know, we use them to form the rows of the matrix now. Of course, we can as well use them to form the columns of a matrix. That means in that case, we'll follow the algorithm for getting a basis of the column space of that matrix. Okay, so it is more straightforward, I think. That is my opinion. So you might find it easier to just use the column space instead. That is fine. Okay, it is easier. I think it is more straightforward also to just put them as the rules. Okay, that's why I'm just adopting that approach here. It doesn't mean that the other will not work. It works. Okay, so this is 1, 4, 0, 6. Then this is 1, 2, minus 1 and 5. Then this is 2, 2, minus 3 and 9. So with this, we have our matrix to deal with, and we now carry out elementary row operations to reduce this. So we have one here, good for us. We can then use that to get rid of these two. So we have this to be R2 equals R2 minus R1. That ensures that this becomes 0. And then for R3, you can say R3 equals R3 minus 2R1. That ensures that this goes to 0. And when we carry out those operations, we have for the first row, nothing is changing. So this is 1, 4, 0, and 6. And then for the second row, we'll have this to be 1 minus 1, which is 0, 2 minus 4, which is minus 2, minus 1 minus 0, which is minus 1, 5 minus 6, which is minus 1. Yep, we good. Then for the next row, that's the last row, R3 minus 2R1. So we have 2 minus 2, that is 0. 2 minus 2 multiplying this, that is minus 8. So this will be 2 minus 8, that is minus 6. Now we have minus 3 multiplying this, that is minus 3 minus 0, so that is minus 3. And then we have 9 minus 2 multiplying this, that is 9 minus 12. And 9 minus 12 is minus 3. Okay, so with that, we are good to go. We now have expressions for this, and then we move to the next one. So this is the non-zero element here on this row. Then we use that to reduce this to 0. Okay, so we can use it as it is. We can also divide through by negative so that this becomes positive, and then we have 2, 1, 1. That works fine as well. So if we do that quickly, that means we set R2 to be equal to minus R2. That is, we multiply through by minus 1. That works perfectly. It makes that look better. So this is 1, 4, 0, 6, and this is 0, 2, 1, and 1. Then this is 0, minus 6, minus 3, minus 3. And with that, we can now think of how do we reduce this, okay, here to 0 using this. So we can say then that R3 equals R3, okay, plus, well, multiply this by 3, we know it gives us 6, so we can say plus 3R2. That ensures that this becomes 6. That's our objective. Sorry, this becomes 0. So when we do that, this will give us nothing is happening to the first row, still 1, 4, 0, and 6. And then on the second row, nothing is happening as well, 0, 2, 1, and 1. And then on the last row, we have 0 plus 3 multiplying 0, that is 0. Minus 6 plus 3 multiplying this, that is minus 6 plus 6, that is 0. Minus 3 plus 3 multiplying 1, that is 0. Minus 3 plus 3 multiplying 1, that is 0. So at the end of the day, we confirm again that the vectors here are not independent. So they span the vector space W, but they are not independent. If we had confirmed that they were independent, then we could also then use this as a basis of the vector space, just as they are. Okay, but now we have seen they are not independent, and at the same time we have confirmed that the vectors given by these first two rules will also span the same vector space, okay, as those spanned by the given vectors, which is W. Okay, so that means the basis of W will be given by the first two rules here. So we conclude that hence basis of W is, so we just interpret them directly. We know the first term is the coefficient of t cubed, so that is 1 t cubed. Second is coefficient of t squared, so this is plus 4 t squared. The third is the coefficient of t, that is 0, so we can ignore that. Then plus 6, which is constant. Then the second is coefficient of t cubed, that is 0, so we ignore that. Coefficient of t, so this is going to t squared, so this is going to be 2t squared. 2t squared. Then the coefficient of t is 1, so that will be plus t, and then the constant is 1, so that is plus 1. Okay, so we can write 2t squared plus t plus 1. So that is that for a basis of W. So obviously W is two-dimensional because there are two vectors in a basis of W. So with this, we conclude that dimension of W, because that is also needed, is 2. Okay, and with that, we are good to go. We're done with that part of the problem as well. Okay, so now let's go on to see what next is required of us. We're asked to find a basis and dimension for u plus w. So for u plus w, we've seen the definition of u plus w already for the addition or sum of two vector spaces. We know that, so in this case, we're given, in this case, u plus w. We know that u plus w, okay, we know it is equal to, so just recall the meaning of u plus w, the sum of two vector spaces from what we've done is the vector space that contains those vectors b, okay, which is b equals u plus w, okay, b equals u plus w, such that U is in U and W is in W. Okay, it contains those vectors V that are equivalent to U plus W. Okay, such that U is an element in U and W is an element in W. So if that is the case, we have also seen that by implication, this means that it is going to be equal to the span of, okay, it is going to be spanned by all of the vectors that span u and w. So at this point, we can use, since we have obtained them already, we can use this basis here. I mean, this basis of w spans w, and it is also linearly independent. That's the difference between this and what we started off with here. This spans w. I mean, that's the meaning of w is equal to span of this, or the vector space spanned by this set. So this set spans W, but it's not independent. Okay, so that's the difference between that and what we obtained here, and that similarly applies to what we obtained for U. Okay, so we can as well just insert them here. That means that W is equal to span of this, just as it is also equal to the span of this. So we can put that here as it is. We can also use, that means we can use these bases right here. It doesn't hurt at all. It will give us the same result. We can also use the spanning vectors as provided. We can use them directly. So just that if we use them directly, which is totally okay, we would have to deal with we'll have to deal with three vectors from this and also three vectors from that, which will be six vectors to deal with altogether. You may say, okay, that is quite much, or that is not much. Okay, anyhow you see it is fine. And we may also just ignore all of that and deal with this. Okay, that makes it compact to work with. Okay, so if we use this, we'll be dealing with less vectors. We'll be starting off with less vectors, and so it will be easier to operate on. Instead of having six vectors, we'll have just four vectors, and then we'll be able to just get the row echelon form. Okay, more quickly. So I'm going to, which should I use now? I'm going to adopt the spans, okay, the basis, or for the basis we have found for each of these, okay, vector subspaces. Okay, that is good. Okay, should we use that? No, let us not use that. Let us use this. The reason for that is because you might actually genuinely come across a situation where you do not have to get a basis for U and W separately first. So if you come across something like that, you will not have to go through this process first. Okay, the reason we're going through this process first is because it is required of us to firstly find a basis and dimension for W. Okay, so it is not always required. So if it is not always required, then any set of vectors that span W can be put together, that span U and W can be put together here to define the span of U plus W. Okay, so let us just put them all together. So let me copy that out and just write them here. All of the vectors now put together. Alright, so U plus W will be spanned by all of the vectors. So these first three vectors are the span of vector space U as we are provided in this problem statement, and the last three are those that span W as provided in the problem statement. Okay, so with that we know U plus W is spanned by all of this, and if we're going to put that in this format, we can easily say that using this structure, this is 1, 4, minus 1, and 3. Right, so we have written them out in this format, and so we can easily get a basis. So we know that these vectors span U plus W. So we now say that hence a basis for a basis for U plus W will be given by this. So let's also put the vectors now in a matrix. So I'll use them to form the rows of a matrix. Then we know that a basis of the row space will be a basis of the vector space or subspace U plus W. So 1 4 minus 1 3 1 5. Okay, so we have now arranged them in rows, okay, to form the rows of this matrix. Okay, so we know that by the time we do row reduction, we identify the non-zero rows. Those will form a basis of U plus W, which is perfectly okay. So we can proceed with this, reduce this to row echelon form, and then get a basis of the vector space from that. That is the vector subspace U plus W. However, we won't follow that approach here. So you can follow that for yourself as an exercise. So you can take that as an exercise for you and just reduce that. Okay, put it in row echelon form. Okay, and check for the non-zero rows there, extract them. That and from those vectors you form a basis of the vector space U plus W. But what are we going to do here together? We're going to put this in a column. Okay, we're going to use the column space instead. Okay, it is not going to give us exactly the same set of vectors. I mean, we've seen stuff like that previously, but it will give us the same results, an equivalent set of vectors that span the same vector space. So we have two sets of vectors that are equivalent in that they span the same vector space at the end of the day, and we have the vectors will have the same number of elements. So that's the same. The sets, those bases, will have the same number of elements because that will be the dimension of U plus W. Okay, so We want to take that column approach because of something we will come back to make reference to, okay, after this, okay. So arranging them in a column, so we can say this is what we get when we arrange them in rows, okay. So when we arrange them in columns, that is, we make the vectors the columns of this matrix, then we'll have, instead of this being on a row, we have 1, 4, -1, and 3. 1, 4, -1, and 3. Then this is 1, 5, 0, and 5. We're using column vectors instead. So this is 3, this is 10, this is -5, and this is 5. This is 1, this is 4, this is 0, and this is 6. Then this is 1, this is 2, this is -1, and this is 5. Okay, 1, 2, -1, and 5. And then we have this is 2, this is 2, this is -3, and this is 9. So that is what we have when we arrange them in a column or in columns, okay, to form the columns of a matrix, okay. So with these, we now carry out elementary row operations on this column, reduce it. So how do we do that? We have 1 here. We're going to use that to reduce all of these to 0. So for the second row, we have R2 to be equal to R2 minus 4 R1. That ensures that this goes to 0. Then R3 will be equal to R3 plus R1. That ensures that this goes to 0. And then for the last one, we have R4 to be equal to R4 minus 3 R1, which ensures that this goes to 0. And by the time we deal with that, what do we have? The first row, nothing is happening there, so we have that to be 1, 1, 3, 1, 1, and 2. Okay, so we're good with that. And the second row, we have 4 minus 4, that is 0. 5 minus 4, that is 1. Then 10 minus 4 multiplying 3, that is 10 minus 12, that is minus 2. 4 minus 4, that is 0. 2 minus 4, that is minus 2. Then 2 minus 4 multiplying 8, 2 minus 8, that is minus 6. Okay, 4 multiplying 2, please. That is 2 minus 8, that is minus 6. And then we go to the next one. It says R3 plus R1. Minus 1 plus 1, that is 0. 0 plus 1, that is 1. Minus 5 plus 3, that is minus 2. 0 plus 1, that is, R3 plus R1, that is 1. Then minus 1 plus 1, that is 0. Minus 3 plus 2, that is minus 1. Yes, we good. Then on the fourth row, we have 3 minus 3, that is 0. Then 5 minus 3, that is 2. We have 5 minus 3 multiplying 3, that is 5 minus 4, that is 5 minus 9, sorry, that is minus 4. Okay. So what else do we have? We have 6 minus 3, so that will be 3, right? 6 minus 3 multiplying 3. 3 multiplying 3 is, 3 multiplying 1, okay, 3R1. 3 multiplying this is 1. 6 minus 3 is 3. Yes, we're good. And then this is 5 minus 3, so that is 2. And then this is 9 minus 3 multiplying this. 3 multiplying this is 6. 9 minus 6, that is 3. So that is that about that. Okay, so we have minus 6. 9 minus 6 is 3. Yep, we're good. So we can now go ahead and reduce this even further. So we come here, the first non-zero here is 1, so we use that to reduce everything below it to 0. So this will go R3 equals R3. So we have this to be R3 equals R3 minus R2. We're using R2 now, so we just want to show this goes to 0. Then for the fourth one, we have R4 to be equal to R4 minus 2 R2. And when we deal with that, what do we get? We have this to be 1, 0, 0, 0. And then this is 1, 1. Okay, so sorry, let's take them row by row, please. Nothing is happening to the first row, so that is 1, 1, 3, 1, 1, 2. We're good. Then the second row, nothing is going on there, so let us put that in as well. 0, 1, minus 2, 0, minus 2, minus 6. And then this is R3 minus R2. So 0 minus 0, that is 0. 1 minus 1, that is 0. Minus 2 minus 2, that is 0. Minus minus 2. And then 1 minus 0, that is 1. 0 minus minus 2, that is 2. And then minus 1 minus minus 6, that is minus 1 plus 6, that is 5. Okay. So then on the last row, we have R4 minus 2R2. That is 0 minus 2, 0. That is 0. 2 minus 2, okay, that is 0. Then minus 4 minus minus 4, that is 0 as well. Then 3 minus 0, that is 3. Then 2 minus 2 multiplying this. So 2 multiplying this is minus 4. So 2 multiplying this is minus 4. 2 minus minus 4, that will give us 6. And then we have 3 here. Minus 2 multiplying this, that will be 3 plus 6, 3 plus 12. So that is going to be 15. So that's what we get at the end of the day. And what else do we do? You can see the next, so this is a non-zero, this is non-zero. The next non-zero elements here, that is 1. So we use this one to reduce everything below it to 0. So to do that, we say this is R4 equals R4 minus 3R3. That ensures that this goes to 0. Okay, and with that we are good to go. So what do we get at the end of the day? We'll have nothing's happening to the first row, that is 1 1 3, then 1 1 2. We good? Then the second one we have 0 0 minus 2 0 minus 2 minus 6. And then for the third row we'll have 0 0 0, then 1 2 and 5. Then on the last row we have 0 0 0, because we're doing R4 minus 3 R3. Okay, so this portion, so 3 minus 3 multiplying 1, that is 0. 6 minus 3 multiplying 2, that is 0. 15 minus 3 multiplying 5, that is 0. So at the end of the day we will arrive at this. So this is the row echelon form of the matrix, okay, which was formed by arranging those vectors that span u plus w in columns. Okay, so we have arranged the vectors here in columns. That means that basically we're interested in the basis of the column space of B. Okay, that is what we're dealing with now. So, and we know the algorithm for getting a basis for the column space of B already. We're going to identify what is the first non-zero element in each row. So the first non-zero element here in the first row is this. Good. The second row, what is the first non-zero element? This is it here. And so this is 0. Please, sorry, this is a mistake here. This is 0 1, so we add 1 here. Yep, this is 0. Yep, we're good. So this is the first non-zero element. This is it here. The first non-zero element in the third row, that is it here, and that is all. The others are 0 completely. So with this, we have been able to identify that from the original matrix, the first column, which will be the vector corresponding to the column that carries the first non-zero elements here, okay, then the second column, and then the third column. So we'll be picking those columns. So we'll pick the first column, so we can just take note of that. We'll pick the second column, and we'll pick the first column. Okay, so and those when put together will form a basis of the vector space. So that's all we're going to do now. 1 2 and 4. Okay, 1 2 and 4. So we now say that therefore, so we now say as a basis of u plus w, a basis, this is a basis, a basis of u plus w is given by, so we'll pick those vectors. What will those vectors be? The first vector, so we're going to the original matrix now, going back to the original matrix. So that will be 1 4 minus 1 3, and then 1 5 0 5. So 1 4 minus 1 3. So we'll pick that 1 4 minus 1 3. So 1 is the coefficient of t cube. 4, that's the coefficient of t squared. So that will be 4t squared. Minus 1, that is the coefficient of t. Then 3, that is the constant. Okay, so that is 1 4 minus 1 3. which is the column corresponding to this that has the first non-zero element here. And then we have the next one, which is the second column. So we'll go back and pick from the second column. We have 1505, 150, and 5. So 1, that is t cube, 5, that is plus 5t squared, 0, that means plus 0t, then plus the constant 5. We've ignored t because that coefficient is 0, so this is plus 5. And then for the last one, we'll pick the fourth column. So we'll go ahead and look for the fourth column here. This is column 1, column 2, column 3. This is column 4. 1, 4, 0, and 6. So for that, we have 1, 4, 0, and 6. That is t cubed plus 4t squared, then 0, that's a 0t, then plus 6. Okay, so 1, 4, 0, and 6. That is what we have on the first column here. And with that, we are good to go. We have now found a basis for u plus w. Okay, so we say that ends a basis of 4 is this. Okay, and obviously from this we can see that the dimension of the vector space u plus w is equal to 3, because the basis of the vector space has has 3 vectors, as we've now found them. Okay, so with this we are good to go. So you could have followed this approach, as we noted here. You could take this as an exercise, reduce this to echelon form, and get the non-zero rows there, use them to form a basis for the vector space. That means if you reduce this to echelon form, row echelon form, this row vectors arranged here to form this matrix, you would have only 3 non-zero rows at the end of the day. So um, that means expectedly all of this will go to 0. Okay, so you can give that a try for confirmation at your end. Okay, so we're good for this part of the problem, and we can proceed to the next one. But before we do that, we know that there is an alternative way to get a basis for u plus w. Okay, yes, this is correct. This is totally fine and acceptable. And we could have followed this approach as well to get a basis of the row space of this matrix, which is fine and also acceptable. Another thing we could have done, which we stated when we started off, was that we could have started off with span of basis vectors that we already had for u and w, so that will reduce the number of vectors we would have to consider altogether. That would have reduced the number of vectors we had to consider to 4 instead of 6. Okay, and that would also give us a correct basis for the vector space u plus w. So that is an alternative approach. Okay, so let us quickly have that alternative considered here. So we can say that to this portion, alternatively, we can say that u plus w equals the span of, so this time around, instead of starting off with those vectors which we know that are linearly dependent, we can start off with the vectors which we have firstly reduced to obtain a basis for u and w. So we know that u is spanned by this. That is why it is a basis. Okay, just as u is spanned by the vectors we started off with here. So we can just copy this out from u t cubed plus 4t squared minus t plus 3. So let's write that out. T cubed plus 4t squared minus t plus 3. All right, so these are the vectors formed directly from the basis we have obtained for u and w. So we know that u plus w will be spanned by these vectors, okay, just as it is spanned by these vectors. What is the advantage of using these? We have less vectors to work on, okay? So at the end of the day, we must arrive at the same conclusion. Yes, not exactly the same set of bases, okay? If it happens, good. If it doesn't, not likely to happen, good as well. But both of them will span the same vector space, u plus w, at the end of the day. And the dimension we get from this also will be 3. So again, we can put this in that vector form. Okay, please observe that these first two came from the basis we found for u. Okay, 2q plus 4t squared plus 6, and this, that's what we wrote out here in the first two vectors. Okay, and then the last two are those from the basis we found already for w. Okay, which is this and this. Okay, That means that those two vectors, the first two will span U, the second two will span W. So U plus W will be spanned by the four vectors put together. Okay, and if that is the case, we can also put this in this form and say the coefficients of t cube coming first 1, then 4, then minus 1 and 3. Do the same thing for the others. No t cube, that is 0, that is 1, this is 1, and this is 2. Okay, working with this. And then for the next one, we know we can put that as t cube, that is 1. Then we have t squared, which is 4. No t, that is 0. And then the constant, that is 6. Then for the last one, we have 2. Then no t cube, that is 0. 2t squared, then t, which is 1, and the constant, which is 1. Okay, so this is basically what we are talking about. So this is spanned by these vectors if we put them or look at the structure this way, right? And that, if that is the case, then we can form a column, we can form a matrix by using these as column vectors, okay, for that matrix. So this will be 1, 4, so the first vector as in the first column, 1, 4, minus 1, 3. Then we have this to be 0, 1, 1, and 2. Then we have this to be 1, 4, 0, and 6. Then we have this to be 0, 2, 1, and 1. Okay, so these are the columns of this vector. Sorry, the columns of this matrix are the vectors we have here. Of course, we could have used the rows as well. Okay, so if we use the rows, it makes no difference. We will get correct results from both, and the vectors would not necessarily be the same. That is, the vectors that will form the basis will not necessarily be the same, but they will be equivalent. Okay, and we will have the same number of vectors at the end of the day. But this gives us some advantage. Again, we'll talk about it when we get there. Okay, so for this we have 1 already, so we get this to 0, get this to 0, and get this to 0. So for that, we say R2 equals R2 minus 4R1. That ensures that this goes to 0. And then for this R3, we can say R3 equals R3 plus R1, because that ensures that this goes to 0. And then R4 equals R4 minus 3R1. And by that, let's have an additional page to proceed. We now say that this will give us, let's write that out quickly. The first row is 1, 0, 1, 0. Then the second row, 4 minus 4, that is 0. 1 minus 0, that is 1. 4 minus 4, that is 0. Then 2 minus 0, that is 2. Then on the next one, R1 plus R3, this is 0. 1 plus 0, this is 1. And then 0 plus 1, this is 1. 1 plus 0, this is 1. And then on the next one, we have R4 minus 3R1. So this is 3 minus 3, which is 0. 2 minus 3, 2 minus 3 times 0, that is 2. Then 6 minus 2 times 1, that is 4. And then we have 1 minus 0, that is 1. Okay, so with that, we are good to go. What is the next thing? We have 1 here, so we can use that to get everything below it to 0. So this is going to be R3 equals R3 minus R2, and then R4 equals R4 minus 2R2. That ensures that this gets to 0 and this gets to 0. And by that, we have this to be 1, 0, 1, 0. And this to be 0, 1, 0, 2, as nothing is happening over there. Then for this, we have R3 minus R2, 0 minus 0, that is 0. 1 minus 1, that is 0. 1 minus 0, that is 1. Then we have 1 minus 2, that is minus 1. And on the last row, we have 0 minus 0, that is 0. 2 minus 2, that is 0. 4 minus 0, that is 4. Then 1 minus 2, that is 1 minus 2 here, this is 1, and this is minus 2, that is minus 2. Okay, so sorry, that is 1 minus 2 multiplying this. Okay, this is 2 minus 2. 1 minus 2 multiplying this. 2 multiplying this is 4. 1 minus 4 is minus 3. So this is minus 3. And that is that about that. So with this, we can now cross out everything we have here using this entry. So we're going to get that to use that to get this to 0 and then see what happens from there. So this won't be going to 0. That is we're expecting that we should have 0 here. So that means there should be there will be a mistake somewhere in what we have done. Okay, so let's correct that. This is meant to be this R4 minus 3R1. This is 6 minus 3 multiplying 1. That is 6 minus 3. 6 minus 3 is meant to be 3 here. So we should have 3 here. And then R4 minus 2R2 from here, this will be 3 minus 0. That should be 3. So what we have here should be 3. Yep, we're good. So with this, we can now reduce this to 0. So if we do that, we have R4 equals R4 minus 3R3. Okay, that ensures that this goes to 0. And when we do that, we have this to be 1, 0, 1, 0. And then this is 0, 1, 0, 2. And then this is 0, 0, 1 minus 1 because nothing is happening over there. And then by this, we'll have this to be 0, 0. So this is 0, 0. 3 minus 3, that is 0. Minus 3 plus 3, that is 0 as well. So at the end of the day, we see that we have one row that is completely 0, and we're good, no problem. Then we know we have used column vectors here, so we have to get a basis of the column space of this matrix. And how do we go about that? Identify the first non-zero element or non-zero entry in each row. This is a non-zero entry. This for this row, it is the first non-zero entry for the first row, the first non-zero entry for the second row, that is this, the first non-zero entry for the third row, that is this. The first one does not have any non-zero entry, so we're good. So that means we're going to pick the first column, okay, for the matrix, pick the second column, and also pick the third column, okay. And when we put all of those together, they will span the vector space u plus w, and they will be linearly independent, okay. So with that, we are good to go. We can now go ahead and pick them. Those will be the vectors 1 4 minus 1 3 0 1 1 2 1 4 0 6. So with that, we now say that, and so we reach the same conclusion here again now, that the dimension of u plus w is actually 3. Okay, so we now say that as a basis from here, a basis for u plus w is, so what would that be? So let's write out the vector. So this means we'll pick the vector corresponding to the first column in the original system here. That is 1 4 minus 1 3. So we put that in its context. 1 4, that is 1 t cube minus 4 t squared minus t, then plus 3. Okay, 1 4 minus 1 3. Okay, this is meant to be plus 4. Okay, 1 4 minus 1 3. We good. Then the next one, that is the vector in the second column, that is 0 1 1 2. That will be 0 t cubed plus t squared plus t plus 2. So we have t squared plus t plus 2. So that is t squared plus t plus 2. We good. Then the vector corresponding to the third column. So here we have 1 4 0 6. That is t cubed plus 4t squared plus 6. T cubed plus 4t squared plus 6. So we write that out as well. T cubed plus 4t squared then plus 6. And that is that about that. We have now another basis for u plus w. This is acceptable, it is correct, just like what we obtained earlier is correct. And again, we confirm from here that the dimension of u plus w, which is the number of vectors in its basis, is equal to 3. Okay, so with this, we are good to go. We can now go ahead and compare these two. Will they span the same vector space? Look at this. This is t cubed plus 4t squared minus 3 plus 2. Okay, so it's the same thing for the first vector here. They don't necessarily have to be the same, okay, but it just happens in this case that they are the same. And the next one here is t cubed plus 5t squared plus 5. That is obviously not the same thing as this. This one is t cube plus 4t squared plus 6. And then the next one after that, t cube plus 4t squared plus 6. Okay, they have these two in common. t, t cube plus 4t squared plus 6 is here, and it is also here, t cube plus 4t squared plus 6. So we're so lucky. And then this one is the only thing now that is not the same as what we have here. T squared plus t plus 2 is not the same thing as what we have here. But is that a problem? Not a problem. How can we confirm that this is still an acceptable result? We should be able to get this by a linear combination of the vectors here. That is what is important. We should be able to get this third vector here. Indeed, all of these vectors should be linear combinations of all of these vectors here. So we can ask ourselves just a kind of confirmation, can we possibly get t squared plus t plus 2 from this set of vectors? If we have t squared, that means there is no t cube term. So if we want to have t squared plus t plus 2, that means there is no t cube term. Can we say, for instance, if we're going to combine these two, what is going to happen? You can see that if we pick this as vector A, and this as vector b, if we do b minus a, what are we going to get? That's basically is b 1b minus 1b minus 1a then plus 0c, for instance. That's the linear combination of these vectors. Okay, one multiplying this, let's say alpha 1 v1. So alpha 1 here is 1, and then this is minus 1. Okay, this is minus 1, this is 1, and then this is 0. So if we do something like that, okay, we'll see that t cube, so b minus a, that is t cube minus t cube, that will be 0 t cube. Then 5t squared minus 4t squared, that will be giving us plus 1t squared. Then we have 5 minus, so we have this doesn't have t, so 0 minus minus t, that will be plus t. Then 5 minus 3, that will be 2. So we have t squared plus t plus 2. So we can see that it is a linear combination of these first two. Okay, t squared plus t plus 2. So that confirms for us that we are on point. Okay, the two sets will span the same vector space. Okay, so we're good. We are good to go. Right, so what advantage does this give, and why do we put it in column form? We will see that as we proceed with this analysis. So for now, let us move on with the analysis and see what we're going to get from it. Okay, so moving on, we say that for the third part, or for the fourth part of this problem, it is required that we obtain a basis and dimension for U intersection W. So how do we go about that now? Okay, so let us quickly deal with that. So that is now the D part. So this is an alternative solution to the C part. So we can just separate it out like that. So we now want to consider U intersection W. So we know U intersection W equals the vector space containing those vectors V, such that V is in U and V is also in W. So V is in U, V is in W. That means we can write V as a linear combination of the vectors that span U. And also we can write it as a linear combination of the vectors that span W. So because of that, we know U is spanned by these vectors we have just obtained, so we can just use them directly here. So we know U is spanned by, what is that result we got from here? T cube plus 4t squared minus t plus 3 and t cube plus t plus 2. So we can just insert those vectors here. So it will be alpha 1, okay, multiplying that. So let's quickly write those vectors out. So B can be written, so we just copied out the vectors in the basis that we obtained for each of U and W. So since an arbitrary vector V in U intersection W belongs in both U and W, then it can be written as a linear combination of the vectors that span U, just as it can also be written as a linear combination of the vectors that span W. So that's what we have used here. We have used two different notations here, so because the coefficients here would be clearly different from those here. I mean, the two sets are different. Okay, so the vectors here are different from those here. So definitely the coefficients here will be different. Okay, that's why we've used a different set of notations for that. So we know that this definitely will hold true for some scalars alpha, for some scalars alpha 1, alpha 2, beta 1, beta 2. Okay, in of course R, because the field here is defined over the field of, I mean, the vector space here is defined over the field of scalars R. That's what's meant by over R. Okay, P of T over R. Yep, we're good. So let's move on. With this, we now say, okay, if this satisfies this relationship for some alpha 1, alpha 2, beta 1, beta 2, how can we obtain these values? So let us now focus on this relationship. If we do that, on this side, we get the coefficients of t cube and equate to the coefficient of t cube on this side. Okay, that will give us an equation. We do the same thing for t squared, we do the same thing for t, we do the same thing for the constants. Okay, so with that, we have enough relations to now see what alpha 1, alpha 2, and also beta 1, beta 2 should look like. Okay, so for us to proceed with that, from this, we simplify this. We're going to have this to be alpha 1. The coefficient of t cubed here is alpha 1. Then plus alpha, there is no t cubed here, so that's just alpha 1. So we can say that is alpha 1 multiplying t cubed plus the coefficient of t squared on the left hand side, that is 4 alpha 1. So this is 4 multiplying alpha 1, then this is plus alpha 2. So multiplying t squared, then the coefficient of t. So that's a plus. Coefficient of t here is minus alpha 1. So we have minus alpha 1. Then the coefficient of t here will be plus alpha 2. So that is t. Then the constant. So that is 3 alpha 1. Then plus 2 alpha 2. 3 alpha 1 plus 2 alpha 2. Yep, we're good. So that is equal to, we do the same thing for this side. C cube is here, it is not here, so that is just going to be beta 1, okay, multiplying t cube, good. Then the next one is, we have this to be 4t cube, and well, 4t square, when we use to multiply this, we have plus 4 beta 1, then for this we have 2 beta 2, so this will be plus 2 beta 2, multiplying t squared. Yep, then there is no t here, but there's t here, so we can have plus, this is going to be beta 2 multiplying t, so this is beta 2 multiplying t. Then the constant here, we have plus 6, okay, beta 1, so we have this to be 6 beta 1, then plus 1 beta 2, so this is going to be plus beta 2. And with that, we're good. We can now equate the corresponding coefficients. So we have the coefficient of t cubed here is alpha 1. So this tells us alpha 1 equals beta 1. We're good. Then the second one tells us 4 alpha 1 plus alpha 2 equals the coefficients here 4 beta 1 plus 2 beta 2. We're good. Then the third one, the coefficient of t, tells us that we have minus alpha 1 plus alpha 2, that's what we have here for the coefficient of t, is equal to beta 2. And then finally, let us have an additional page to proceed. We have the constants giving us 3 alpha 1 plus 2 alpha 2 equals 6 beta 1 plus beta 2. So this is 3 alpha 1, okay, plus 2 alpha 2. That is the constant on the left hand side, and the right hand side will give us 6 beta 1 plus beta 2. So we now have 4 equations. How many unknowns? 4 unknowns. We need to get alpha 1, alpha 2, beta 1, and beta 2. So 4 unknowns, and we have 4 equations. Okay, so we can arrange this properly and solve. We have a system of linear equation, or a linear system of equations now. So we can say that this is going to give us alpha 1 for the first part minus beta 1 equals 0. So let's say we want to arrange them in the form alpha 1, alpha 2, beta 1, beta 2. That means we have alpha 1 plus 0 alpha 2, then minus beta 1 plus 0 beta 2 equals 0. Then for the second, we have this to be 4 alpha 1 plus alpha 2 minus 4 beta 1 minus 2 beta 2 equals 0. We good. Then for the third, we have minus alpha 1 plus alpha 2. There is no beta 1, so we can put plus 0 beta 1, then minus 2 beta 2. Okay. So that's minus beta 2, please. I'll move beta 2 to the other side here. Okay. So that is going to be equal to 0 as well. And for the fourth equation, we have 3 alpha 1 plus 2 alpha 2 minus 6 beta 1 minus beta 2 equals 0. So we have a homogeneous system of linear equations here. Okay, so by this, we can put this in matrix form. The coefficient matrix here will be 1, 0, minus 1, 0. So we have 1, 0, minus 1, and 0. Okay, then this is 4, 1, minus 4, minus 2. We have 4, 1, minus 4, minus 2. And then for this, we have minus 1, 1, 0, minus 1. And for the last one, we have 3, 2, 3, 2, then we have minus 6, and then minus 1. Okay, so this closes this, and with that, we know this will be multiplying alpha 1, alpha 2, beta 1, beta 2. Okay, beta 1, beta 2. And this will be equal to 0. So this is 0, 0, 0, 0. Okay. And with that, we are good to go. We can now do a row reduction on this so that we have it in echelon form, and then we can simplify to see what values of alpha 1, alpha 2, beta 1, beta 2 will satisfy this equation. Okay, so by the time we deal with that, we will have an expression like this. So we have 1, 4, minus 1, and 3. This is 0, 1, 1, and 2, minus 1, 4, minus 4, 0, minus 6. We have 0, minus 2, minus 1, minus 1. And by the time we carry out elementary row operations here, I want to get this to 0. So does this look familiar? Does it look like what we have here? Here we have 1, 4, minus 1, and 3. We have 0, 1, 1, and 2. So that is it here. Okay, the only things that have changed is that here we had 1406 and on the third column there, and now we have minus 1, minus 4, 0, minus 6. It's like we've taken the negative of that essentially. And then on the last column here, okay, the one we just did now, we had 0, 2, 1, and 1. Now we have 0, minus 2, minus 1, and 1. And that is because we have chosen to move all of these to the left hand side. Okay, so moving those that carry the second one to the left hand side give us these negatives. Okay, so we're good. Let's move on anyways. So what does this give us? We carry out elementary row operations, so R2 should be equal to R2 minus 4 R1, so that this goes to 0. Then R3 will be equal to R3 minus, so that's R3 plus R1, please. So that will go to 0. And then this will be R4 equals R4 minus 3 R1. That ensures that this portion goes to 0. Okay. And with that, we are good to go. And this gives 1, okay, 0, minus 1, and 0 on the first row because nothing is happening on the first row. And we have 4 minus 1 multiplying 4, that is 0. 1 minus this, that is 0. Minus 4 minus this, that is minus 4 plus 4, that is 0. What did we just do? R2 minus 4, that is 1 minus 0, please, that is 1. Okay, now this is minus 2 minus 0, that is minus 2. Okay, then what is the next thing to do here? We have this to be minus, we have this to be R3 plus R1, that is going to give us 0 here. 1 plus 0, that is 1. 0 plus minus 1, that is minus 1. Minus 1 plus 0, that is minus 1. Then we have here R4 plus minus 3r1, this is 0. 2 minus 0, that is 2. Minus 6, okay, plus 3, that is minus 3. And then minus 1 minus 0, that is minus 1. Okay, so what do we have at the end of the day? So we have 1 here. We will use this to reduce everything here below it to 0. And for that, we'll say R3 equals R3 minus R2. R4 equals R4 minus 2R2. And when we do that, we will obtain the following: 1 0 minus 1 0, because nothing is happening here. Then this is 0 1 0 minus 2. Then this is 0 minus 0, that is 0. 1 minus 1, that is 0. Minus 1 minus 0, that is minus 1. Minus 1 minus minus 2, that is minus 1 plus 2, that is 1. And then for this we have 0 minus 0, that is 0. Then 2 minus 2, that is 0. Minus 3 minus 0, that is minus 3. Then minus 1 minus minus 2, that is minus 1. Then minus minus 2, that is negative of this. Minus 2 multiply minus 2, that is 4. Okay, so we have minus 1 plus 4, and that is 3. Okay. So then at the end of the day, we can reduce this further. So we have 1 here. We can change it to minus 1. We multiply through by 1. We can also use it as it is and get rid of this directly. So this will give us R4 equals R4 minus 3R3. That will ensure that this goes to 0. Okay. So when we do that, nothing is happening to the first row. That is 1 0 minus 1 0. Then this is 0 1 0 minus 2. Then this is 0 0 minus 1 and 1. Then for the last part, we have this to be 0 0 minus 3 plus, that is minus 3 plus 3, so that is 0. Then we have 3 minus 3, that is 0 as well. So with that, we are good to go. We now have this in echelon form, so we can get back to the equations with alpha 1, alpha 2, beta 1, beta 2. So we can now say that, therefore, having reduced this now, we ensure that what we have here is 1 0 minus 1 0, 0 1 0 minus 2, 0 0 minus 1 1. Then we have 0 0 0 0. Then multiplying alpha 1, alpha 2, beta 1, beta 2. So can close that. We know that is equal to 0 0 0 0. So with this, we are good to go. What do we do now? We can expand this out. So this will give us alpha 1 multiplying this. So this is minus alpha minus beta 1. So we have alpha 1 minus beta 1 equals 0. Okay, that remains unchanged. This is 0 here multiplying alpha 2, 0 multiplying beta 2. And then on this we have alpha 2, that's 0 alpha 1 plus 1 alpha 2 plus 0 alpha 0 beta 1, then minus 2 beta 2. So we have basically alpha 2 minus 2 beta 2 to be equal to 0. Good. Then on the third row, we have minus 1 and 1. So this will correspond to minus beta 1, then plus beta 2 equals 0. And then on the last row, we have just 0. So that's 0 equals 0. Obviously, that is true. 0 is indeed equal to 0. So we have these equations now to deal with. We can now see that we have 3 equations basically and 4 unknowns. That means we have one free variable, so we can choose whatever we want to use as our free variable here. But of course, as we noted in a previous chapter, it is usually better if we see that this is a pivot column, this is a pivot column, this is a pivot column. We can choose the variable that corresponds to this that is not a pivot column. That's good. And that will be beta 2 in this case. So we can set beta 2 to some arbitrary value. So we can say set beta 2 to k. So if we set beta 2 equals k, then what will happen to the others? So from here, using this equation, so let's say this is equation Roman figure 1, equation Roman figure 2, and equation Roman figure 3. Then from equation Roman figure 3, we're able to get beta 1. This is beta 1 equals to beta 2. That means beta 1 will also be equal to k. We good. Then we know that beta 1 itself using equation 1, Roman figure 1, we're able to see that beta 1 is the same thing as alpha 1. So we see that alpha 1 is equal to beta 1, which is also k. And then from that, we can set the expression into alpha 2 so as to get alpha 2 using equation Roman figure 2. We know that this will give us what is that? Alpha 2 equals 2 beta 2. So beta 2 is k, that will be 2k, right? So that is that about that for alpha 1, alpha 2, beta 1, and beta 2. Yep, so we have our values for alpha 1, alpha 2, beta 1, beta 2. Okay, in terms of a parameter k, that means k can take on any arbitrary value. Okay, and that would still satisfy this equation. For instance, k can be equal to 1. If k equal to 1, then beta 1 will be all of this will be 1 except for alpha 2, which will be 2. And we can check that that will satisfy this equation we started with. If they are all 1 except for alpha 2, which is 2, this will be right here 1 minus 1, which is 0. Okay, this is 1. This one is 1 as well. They will cancel out. And then we have alpha 2, which is 2. This is 1. So 2 minus 2 will also cancel out. And if we check for this, 1 and minus 1 for this, and then this is 1. That those will cancel out. Then we have minus beta 2. That is going to give us minus alpha 1 plus alpha 2. This one give us that. Okay, alpha 2 is 2. Okay, so this is minus 1 and then plus 2. Yep. So this is 3. This alpha 2 is 2. So this is 4. Then we have this to be minus 6. Okay, minus 1. That is minus 7. Then plus 3. Then plus 4. That will give us 0. So that is a confirmation for us. Then, what is the meaning of this? We have just said V, which is an arbitrary element in U intersection W, is given by alpha 1 multiplying this plus alpha 2 multiplying this. So we can then substitute that back here. We know if we substitute alpha 1, alpha 2 here, it will give us the same thing as when we substitute beta 1, beta 2 here. Okay, I mean, that is the whole point of this solution that we have just obtained now. So we can now say that that means an arbitrary element V in U intersection W can be written as K1 because we have gotten this to be K1. We're multiplying this plus 2K because we got this to be 2K now. Okay, multiplying this. We know we got our result in terms of some parameter K. Then we can put those together. We could also use K multiplying this plus K multiplying this. Both of them must give us the same result. That is the whole point of the result we are just obtained. So we now say that using this in the expression we started off with here, so maybe we should denote this as some equation, say equation star, so that we can now make reference to it. Okay, so using equation star now, we know that an arbitrary element in the set U intersection W, that is the subspace U intersection W, will be given by alpha 1 is now k into, so what is that vector up there? Okay, that's alpha 1 multiplies, that is t cubed plus 4t squared minus t plus 3, t cubed plus 4t squared minus t plus 3. So we have t cubed plus 4t squared minus t then plus 3, then plus alpha 2 is 2k. We got that to be 2k, so that will be multiplying the vector which was the coefficient of alpha 2 in equation star. So what is that? That is t squared plus t plus 2, t squared plus t plus 2. So this is t squared plus t plus 2. Okay, so if we put these two together, we know it will be equal to the other one as well, so we could use the other one. Okay, we know any one of them will give us the same result in terms of k, so we can just put all of this together. K is common to both of them, just leave out the k, then this will give us 1. Okay, so this will be k into t cubed. There is no t cubed here, so we just forget about that. Then plus, what do we have here? This is this is 4t squared. This will be giving us 2 multiplying t squared. Okay, so this is going to be 6t squared altogether. Don't forget we're factoring out everything. Okay, so when we factor out k from both of them, this will be t cubed plus 0t cubed. That's how we came about t cubed. This will be 4t squared plus 2t squared. That's how we came about 6t squared. And then we have this to be minus t plus 2t. That will be plus t. Then what do we have left? We have this to be 3, then plus 2 multiplying this. That is 2 multiplying 2, which is 4. That will be plus 7. So this is what we have at the end of the day. So with this, we can see that an arbitrary element in U intersection W is given by a scalar multiple of this vector. This is a vector on its own. Okay, so with this, we now have a basis of the vector space, because this tells us that any element V in U intersection W will be given by K into T cubed plus 6T squared plus T plus 7. So that means t cubed plus 6t squared plus t plus 7 generates the vector subspace U intersection W. And we could obtain this same result if we used the second part of that equation star. For instance, from what we have just obtained, we have seen that beta 1 is k, beta 2 is k. So if we did that here, we would see that if we substituted k here, we would have this to be k into t cube. Okay, there's no t cube here, that will be t cube. Then this will be k for both of them. So this will be 4t squared plus 2t squared, that is 6t squared. And then for the other type, for the others, for t, there is no t in the first one, so that will be plus t. So we'll have t cube plus 6t squared when we add these two up, then plus t, then plus 7, which is exactly the same thing as what we have just obtained now. So either of them that is used to give us the same result. So this tells us that an arbitrary element V in the subspace U intersection W is given by t cubed plus 6t squared plus t plus 7 multiplying some arbitrary constant. So this is a vector which generates for us our subspace U intersection W. So we now say that this implies that the subspace U intersection W is generated by this vector. So it is generated by the vector t cubed plus 6t squared plus t plus 7. So that is to say, the meaning of this is that it has a basis of U intersection W is that singular vector, the set that contains that singular vector, which is t cubed plus 6t squared plus t plus 7. Okay, so with this, we are good to go. We now have a basis of U intersection W. How do we know this is a basis? Every vector in U intersection W, as you have now seen, can be written as a scalar multiple of this singular vector. If it were that we had maybe another k2 here, maybe k1 and k2, then we would write the result here as a linear combination of k1 k2. So in that case, we'll be able to tell that every element in V is generated by whatever two vectors we then have to be the coefficients of k1 and k2. But in this case, we have only one vector, and of course a vector with itself that is linearly independent. There's no other thing to compare it with. Okay, so this is the set that generates this vector subspace U intersection W, and that confirms also, or that tells us that the dimension of the subspace U intersection W equals 1. Why? Because we have only one vector in its basis, and this is that basis of the vector subspace U intersection W. So this is the process to follow every time and anytime we have to solve this problem. Okay, so that is our result. That is all that is required of us in this problem. We now have a basis of U intersection W to be this. We have the dimension of U intersection W to be 1. We have the dimension of U plus W right here to be 3. We have a basis for it. We also used an alternative method where we just use the vectors that span the vector spaces u and w directly. Okay, that was what we used here. We saw that it will give us the same result. Okay, so let us make an interesting observation here, which applies generally to vector subspaces u and w, and also uh, their sum and intersection. Okay, so we're done with the solution to this problem. Okay, we just want to make some remarks here. Actually, this is a theorem that could also be established rigorously, but we will here only state this theorem, that the dimensions are related by this. If you have the dimension of u, then plus the dimension of w, it will be equal to the dimension of u plus w plus the dimension of u intersection w, okay, plus the dimension. Okay, let's write everything on a new line to avoid confusion, so that someone doesn't just come across a part of this and let's just think that it is just dimension of u plus w. This dimension of u plus the dimension of w is equal to the dimension of u plus w plus the dimension of U intersection W. Okay, so this is an important result that applies in all cases. Okay, it applies in the specific case we have just considered here. It would apply also in any other case of vector subspaces U and W. Okay, so as we've seen in the results just now, the dimension of u is 2. We just got that up there. Dimension of u is 2. We also saw that the dimension of w is 2. Interesting. And then we saw that the dimension of u plus w is 3. And we have just seen now that the dimension of u intersection w is 1. So dimension of u was 2, so this 2 plus 2 equals 3 plus 1. So that relationship always holds. So please take note of this. It is a very important relation, okay, for sums and intersections of subspaces. Okay, so what other thing can we observe here? Now I want you to pay good attention here, that we got a basis for the vector space U intersection W. You can see how we went through all of this process to get this basis. If we're going to look at this in vector form or in the form that we could put into the matrix, this is 1617. So could we have obtained 1617 another way without going through this process? So let's look at all of the things we've gone through here. None of them could have given us 1617, even though the expression we actually add at the end of the matrix we add after reducing all of this looked similar to what we had when we started off here. Okay, in this case it looks similar, but it is not the same, in that the signs of these last two rows are not the same because we have moved them to the other side. So there is no acceptable or generally acceptable way of just getting the dimension of u intersection w from what we have done here. No, we will always have to go through this process like we just did, okay, or any other process that involves even more rigorous workings. Okay, but this is the simplest and easiest way to just get the a basis of the intersection of the subspaces u and w. If we needed to just get the dimension, that means we wouldn't have to go through this process. We would just get the dimension of u, the dimension of w, the dimension of u plus w, which are very straightforward to get, and then we will take dimension of u intersection w to be equal to dimension of u plus dimension of w minus the dimension of u plus w, and that would have given us 1 if we didn't need to obtain this basis of the vector space u intersection w. But whenever the basis is required, there is no shortcut. You can see that there is nothing elsewhere that could have given us these results here, 1, 6, 1, and 7. Okay, not even in the big matrix that we considered previously. So if you look at this also, it could not have given us 1617 anywhere. That does not even that doesn't show up anywhere in this system. So we always have to go through this process to establish for ourselves what a basis for the vector subspace u intersection w might be. Okay, so with that, we are good to go. So we said that if we just wanted to get the dimension of u intersection w, instead of going through that last step, okay, that long journey, okay, of solving for alpha 1, alpha 2, beta 1, beta 2, we could, if we knew already, we could use the dimension of u, then plus the dimension of w, then minus the dimension of u plus w. And similarly, if we wanted to get the dimension of u plus w, we could just make the dimension of u plus w the subject, okay, from this relationship as well. And that is all for this lesson. We've come a long way. So, thank you for watching. If you watched to this point, you can give yourself some applause. And I'll see you in the next lesson as you consider some other interesting stuff about linear vector spaces.